As your database starts to grow, there's a part of the database design that becomes more and more important, and that's creating and using indexes. An index in a database is like an index at the back of a textbook. It will help you find things in that book. Say if I have a 500-page book on database management and I want to find the content dealing just with date columns, I can look in the back in the index for date. It tells me that's on page 124, and I turn directly to that page. Indexes are all about speed of access. I could have found that content by going through the book page by page, so the index isn't adding any content, it's just helping me find it. And here's the most essential ideas. See, the data in your tables is inherently unstructured and unordered. Sure, all the data in one row is kept together, but there's no particular enforced order to those rows unless you say otherwise. And yes, when we write queries, we can use the order by clause to impose a sequence on our results, but that's not the issue here. The issue is getting directly to certain content, like getting directly to one specific row in a large table. Now you might think, well, hang on a second, didn't we take care of that by adding a primary key to our table? Well, yes and no. The primary key does let us uniquely identify a row, but that's a very different question from does it let us find that row really fast when it's somewhere in the middle of 500,000 other rows? And that's the problem we're trying to fix with indexes. Like with reading a textbook, I don't want to have to leaf through every single page every time. I want to be able to jump directly to the relevant point. So we need an index. And the most basic, the first index that's created, the primary index on any table, is what's called the clustered index. And that means pick a column as the clustered index, and the database will order the data in that table based on that column, meaning that on that physical disk itself, where these rows of data are stored as bits and bytes, they're actually sequenced that way. So the clustered index is almost like having a residential phone book or white pages, where the clustered index in a phone book would be last name. So everyone is listed in the book in alphabetical order by last name. The actual data is structured and presented that way. You don't have to look in the back of the book to find out where the names beginning with D are. You know where they are. They're towards the front between the C's and the E's because the data is ordered that way. And the most common clustered index in any database table is the primary key column, whether that's an automatically generated integer or a unique string or anything else. And actually, most database management systems, when you define a new table, will automatically make the primary key the clustered index unless you say otherwise. And that is usually the best option because we already chose the primary key as a significant way to get to the individual rows. But if you found yourself accessing the data primarily using another column, you might change that column to be the clustered index instead. See, each table can only have one clustered index, the same way that names in the phone book can only be sorted one way. But what you can have more of is non-clustered or unclustered indexes. Here's the situation. I have a basic customer table here with a primary key on the customer ID column, and the clustered index is also on that column. So if I write a query that uses that, a select where customer ID equals query, it's going to be very fast to get there. And there's two things going on. The database engine knows how to identify that row because it's a primary key, but it knows how to get to that row quickly because it's a clustered index. But, on the other hand, if I figure out that we often also access this table using last name, so if I write a lot of queries that look something like this, select star from customer where last name equals Smith, well, that's a different matter because the database management system has no idea physically where in this table where that particular last name might turn up. And that means a query like this would require the database management system to start at the first row and read through every single one, row by row, looking for that piece of data. This is sometimes called a full table scan. It's a very inefficient way to get to your data, and the more rows you have, the worse it gets. Wouldn't be bad with a dozen or a few hundred rows, but once you get to thousands, tens of thousands, hundreds of thousands, it's highly inefficient. So if I have to do this kind of query a lot, where we're actually querying on an unindexed column, it's going to be a problem. And here's one way I can fix it. I can create a secondary index, a non-clustered indexed. This is more like having an index at the back of the textbook. It's created as a separate piece by itself with its own meaningful order. So in this case, I'm imagining I have this index existing. It's sorting now by last name ascending, the way that we can't actually do in the regular table because we're already sorting by customer ID. So we're basically creating a map here of how we can go to last name, in this case, say Smith, find that particular name. It's much easier to get to in the index because the last name is ordered alphabetically. Then we find the location of that in the regular table, and we can jump directly to that place. Now, it's not quite as quick as using the clustered index, as we still do have to read from one place, then jump to another, but it's much quicker than a full table scan. Very useful if you know there's a column you're going to use a lot in your queries. A common thought from people new to database design at this time is usually, well, why don't we just index everything? Why don't we add a non-clustered index to every column so whatever query we write is nice and fast? And that is a really bad idea. Here's why. Every index has a cost. Indexes are a benefit when reading data, but they're a detriment when writing or changing it because they must be maintained. So let's say I've got a table here, pretty typical employee table, and I've got two non-clustered indexes on this table. So the clustered index, the way the data is actually sorted, is based on employee ID. Then I have a non-clustered index on last name and a non-clustered index on first name. Well, this is pretty good. It means when we do a select, I can go by employee ID, I can go by first name, I can go by last name. They'll all be quite fast. But when we write to this table, when we insert a row, we're not only writing data into the table itself, and if your clustered index is on an automatically incrementing number, we just write to the end, which is easy, but every insert we do is going to require another change, a write into every non-clustered index. If I have added this new row of Brenda Daniels, I've added to the table, I now need to go ahead and make a change to the non-clustered index for last name to insert Daniels in there and point to the employee ID or the location that she's at, and then do another insert to make sure that Brenda is inserted on the non-clustered index for first name. So if you started adding even more of this, if you have, say, 5 non-clustered indexes as well as your clustered one, that means that one insert, which started off as one physical write operation to the database disk, is now 6 write operations, and you have made things significantly more inefficient. That's why you don't put indexes on everything. You only put them on the columns that you really need and use all the time. It's far better to do an occasional table scan than have multiple indexes that you don't really use. Now, one of the reasons I don't talk much about indexing up front in the early modeling section of the course is it's an easy mistake to think that you decide your indexes up front and then you're done. Well, it's true you often do select your primary clustered index then with your primary key, but working with indexes is a much more ongoing thing because you often can't tell what the best non-clustered secondary indexes will be until your database has been in use for a while and you figure out how people are really using it and what kind of queries they're really running rather than how you hoped or thought that they'd use it. So indexing is a trade-off. It improves read performance, but at the expense of writing to the database, and also size, as every index will require its own space on the drive. And in a large database, indexing is something the database administrator may spend a lot of time working on as the system grows. But there's one good thing. Changing and tweaking database indexes is something that can be done without breaking any applications that use that database. Because as long as you're not changing column names, all your existing queries should work exactly the same. They'll just get faster, hopefully.